Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Step 1. Identify the starting material. The starting material is 1-methyl-1-hydroxymethyl cyclopentane, a cyclopentane bearing both a methyl group and a CH2O group at the same carbon, C1. Step 2. Reaction A. H plus heat. Acid catalyzed dehydration ring expansion under acidic conditions with heat. The primary alcohol, CH2O, is protonated and loses water to generate a primary carbocation at the exocyclic carbon. This primary carbocation undergoes a 1,2-alkyl shift ring expansion. The C1-C2 bond of the cyclopentane migrates to the exocyclic carbocation, expanding the 5-membered ring to a 6-membered ring and placing the positive charge at C1 of the new ring, which is tertiary. Elimination of a proton then gives methylene-cyclohexane, or, more precisely, after proton loss from the ring carbon adjacent to the cationic center, the thermodynamically favored product is 1-methylcyclohex-1-Na, methylcyclohexane. Actually, tracing carefully, starting cyclopentane C1 has methyl and CH2O. Protonation of A gives CH2+, the ring C1-C2 bond migrates to give a 6-membered ring carbocation at what was C1, now tertiary, bearing the methyl. Deprotonation of an adjacent CH gives 1-methylcyclohex-1-Na, a 6-membered ring with a trisubstituted double bond between C1, bearing methyl, and C2. Step 3. Reaction B. O3Zn, ozonolysis with reductive workup. Ozonolysis of 1-methylcyclohex-1-Na cleaves the double bond. Since the double bond is endocyclic in a 6-membered ring, cleavage opens the ring and gives a single bifunctional compound, a 6-carbon chain, actually a 1,6-decarbonyl compound. The double bond between C1, bearing methyl, so it becomes a ketone end, and C2CH becomes an aldehyde end. Cleavage of the ring double bond in 1-methylcyclohex-1-Na gives a linear dialdehyde ketoaldehyde, specifically 6-oxoheptanyl, CH3C is equal to O, CH2, 3-CHO, i.e., a 7-carbon chain with a ketone at one end and an aldehyde at the other, OHC, CH2, CH2, CH2C is equal to O, CH3. Step 4. Reaction C. O heat. Intramolecular aldol condensation. The ketoaldehyde, B, is equal to 6-oxoheptanyl undergoes intramolecular aldol condensation under basic conditions with heat. The base deprotonates the alpha carbon of the ketone, alpha to the methyl ketone, and the resulting enolate attacks the aldehyde carbonyl intramolecularly, forming a 5-membered ring beta-hydroxycarbonyl intermediate, aldol product, which then undergoes dehydration, heat, to give the alpha, beta-unsaturated cyclic ketone. The ring formed has 5 members. The enolate carbon attacks the aldehyde carbon to close a 5-membered ring. The product after aldol and dehydration is 1-cyclopent-1-N-1-Yl, ethan 1-1, i.e., a cyclopentane ring bearing an acetyl, COH3, substituent on the double bond, which corresponds to option C. Wait. Re-examining, the ozonolysis of 1-methylcyclohex-1-Na, double bond between C1 methyl and C2 gives C1 end ketone, CH3-CoH, C2 end aldehyde, CHO, with a CH2-3 tether between them, OHC, CH2-3-CoH, CH3, 6-oxoheptanyl. Intramolecular aldol, alpha carbons of the methyl ketone, the CH3 or the CH2 next to C is equal to O. Deprotonation of the CH2 alpha to the ketone, C5, enolate attacks the aldehyde, C1, to close a 5-membered ring, atoms, C1, aldehyde, C2, C3, C4, C5, enolate, is equal to 5 atoms in ring. Aldol adduct is a cyclopentanol ketone. Dehydration gives the cyclopentan ring fused with the acetyl. Product 2-acetylcyclopent 2N1-ol after aldol, then dehydration gives 2-acetylcyclopent 2N1-1. No, the aldehyde becomes C is equal to O, ketone in ring if substituted, or aldehyde. The aldehyde carbon becomes part of the ring as C is equal to O, combined with the enolate forming the C bond. After aldol and dehydration we get a cyclopentan with a methyl ketone exocyclic substituent is equal to 1-cyclopent 1N1-Yl, ethanone, option C. Why other options fail? A. Cyclohexane would require a 6-membered ring aldol which would need a 7-carbon dialdehyde, not formed here. B. Cyclopentan without substituent doesn't account for the methyl group from the starting material. D. Has ChO and methyl on a cyclopentene, inconsistent with the aldol product. Therefore, the correct answer is C. Therefore, the correct answer is option C.